the first one that I'll mention is if I've got sigma notation and a constant. So let's say I've got 7 and I'm going from I equals 1 to 10, just for fun. Notation wise, this is saying my argument here is 7, and I'm going to write that down, adding it up because I've got a summation, starting with the first term and going to the 10th. So this would look like 7 plus 7 plus 7, all the way out there 10 times. But if we're clever about this, if there's 10 of those 7s, then the shortcut way to write this is just 7 times 10. And as a general rule, if I'm taking the sum from I equals 1 to n, and I have a constant, then the answer is the constant times n. Another notation, like rule that we've got, is if I'm taking the sum of I, and I'm going from 1 to n, this is a rule, and we talked briefly about where it comes from, or at least why it works. But this ends up being n times n plus 1 all over 2. So what that might look like as an example, if I had something that looked like I'm going from 1 to n, oh, sorry, let me not go to n in my example here. I'm going from, let's say, 1 to 15 of, let me make this I plus 13. Now, let me go one more. Let me make this 2i plus 13. Then I can take this, break it apart into 2 pieces, because I've got the sum of 2 things in here. And I can break that apart to look like I from 1 to 15 of 2i plus my sum from I equals 1 to 15 of 13. And then here, we talked about this last week, but if I've got a constant times something, I can pull that constant out in front of the sum. Because essentially, if I were writing all of these out, they would each have a times 2, and I could factor that out of the entire expression. So here, I can take one more step and rewrite that as 2 times the sum from I equals 1 to 15 of I, plus that sum from I equals 1 to 15 of 13. And now I'm ready to apply my rules and get an actual number. So this one would become, man, I'm gonna squeeze it in, 2 times, and now our formula says to do n times n plus 1. Since our n is 15, that means I'm doing 15 times 16, whole thing over 2. For this one, my formula, because I'm adding up a constant from 1 to 15, and that's a little bit messy down there. Let me actually make that look like equals 1. So I'm going from 1 to 15. That's going to be 13 times 15. And you could throw that whole thing in a calculator, get a number, or if you were doing this as a web work problem, you could just type that in and let web work be the calculator for you. I want to estimate the area from 0 to 2. So I'm going to call that x equals 2 and call that x equals 0. And I want to estimate this area. Now, in terms of geometry formulas, we've got formulas for the area of a circle or a semicircle or a rectangle or a trapezoid or a triangle. But this thing is none of those because it's got that little bit of curvature to it. So one of the ways that mathematicians came up with is, well, we can estimate that area by using a shape that we do know how to find really well. How about rectangles? So if I come in here and I said that I wanted to cut this into 4 rectangles. So right now my width is from 0 to 2. And if I slice that into 4 pieces, we can probably do that math in our heads and say, oh, well, that's going to be 2 divided by 4. They're each going to be a half. But I want to make this messier. and say, let's break this into 3 pieces. Some of you are probably great with fractions and you can super easily see where each of those pieces are going to go. If it's 10:09 on a Monday morning and your fraction brain isn't quite awake yet, then when we're thinking about the width of those rectangles, then I can get that width by subtracting the distance between my endpoints, which we often call like a b minus a, and then dividing that by the number of rectangles. So in this case, the width of each of my rectangles is going to look like 2 minus 0 all over 3, or 2/3. So when I come down here to my picture, I'm going to draw in my I'm going to draw in the spacing for my rectangles. And I know that the width of each one should be 2/3. So that would be 2/3. And then the next one over, I've moved 2 of the 2/3. So I'm now at 4/3. And just as a reality check, when I get to the end, I should have moved 1, 2, 3 of the 2/3. And 2 is 3 of the 2/3. So we're good. The numbers worked out right in terms of that endpoint. Well, what that has defined is the intervals where I'm going to draw in my rectangles. So I've got 3 rectangles here. I'm going to have an area 1, area 2, area 3. But what we have to decide for each of those rectangles, we've got our width, but we need to figure out what height we're going to use. Now that's often, we talk about it as our sampling point or our sampling number. So in this interval, I have to choose what's the point where I'm going to sample the height. So one option is to use right-hand endpoints. What that means is that in each of these rectangles, I'm going to use the wall on the right-hand side to draw in a height. So if I were to use right-hand endpoints, I would draw in my rectangles like this, defining the top of each rectangle to come from the X value on the right-hand side of the interval. Now, in terms of the textbook problems, you're usually told to use left-hand endpoints or you're told to use right-hand endpoints. If it doesn't specify, you can use whatever the heck you want, but the textbook problems all tell us what we're going to use. So if I use right-hand endpoints, then my total area here my first rectangle, I've got a width of 2/3. So I'm going to have like a base or the width times a height. And for that first rectangle, my height is going to come from the X value at the right-hand side. So for now, I could just write that in as F of 2/3. Then for my next rectangle, again, my width is still 2/3. And my height is going to look like F of 4/3 because I'm using the right-hand side of the next interval. And then again, my width is 2/3 because I have an equal width for each of these. And my height on that last one is coming from plugging in X equals 2. And if all we had to do was find an expression for this, maybe we could quit here. Most of the time we need to actually evaluate this. So to evaluate this, I'm going to take that 2/3 and plug it into my function. So this would look like X cubed or 2/3 cubed plus 2. Oops. I used a bracket the first time. Consistency for my notation, I'll use a bracket over here too. Plus 2/3 times F of 4/3. So now I'm plugging in 4/3 and I've got 4/3 cubed plus 2. My last one, 2/3 times What was my last value? 2. So 2 cubed plus 2. And again, this is the point where you're either going to reach for a calculator or type all of the things in. And yes, I would call it a typo, but I'm writing by hand, so I can't blame it on typing. It's a hando. Okay. Thank you for catching my mistake. If I'm coming in here to do left-hand endpoints, then that just means, so nothing changes in terms of my width. It's still splitting it up into 3 pieces. I've got 3 rectangles. So the width of each of them is still 2/3. But now in each of those intervals, rather than using the right-hand side of it to sample the height, I'm going to use the left-hand side of it to sample the height. So when we go to do our area, and I said I was going to factor it differently this time. So when we go to do our area, I've got each of them has a width of 2/3. So I can go ahead and factor that out in front. And then this would just look like I need the height using the left-hand side of my first interval. So plugging in 0 for x. And then the left-hand side of my second interval. And the left-hand side of my third interval. When I plug those in, I will make sure to cube them all this time. The f of 0 is going to look like 0 cubed plus 2. F of 2/3, I'll have 2/3 cubed plus 2. And then f of 4/3, 4/3 cubed plus 2. Now, in terms of these two, the left-hand endpoints or right-hand endpoints, those have given us an overestimate and an underestimate. So here on the left-hand side, it's an underestimate, and we can think about this 2 ways. Each of these rectangles is under the curve. So it's an underestimate. Numbers-wise, it's going to be an underestimate because if I found the true area under the curve using these left-hand endpoints, I'd be missing this part and this part and this part. So that left-hand, using the left-hand endpoints for this graph gave us an underestimate. And left endpoints. So first of all, if I'm going to use 4 rectangles and I'm going from 1 to 3, then I know that the width of my rectangles, I'm going to get, I usually call that delta x, but the width of the rectangle is going to be b minus a, meaning the farthest to the right point, farthest to the left point. So 3 minus 1 all over 4. So that's going to be 1/2. So the width of each of my rectangles is 1/2. And I didn't give us a function this time, so we just have to use our best guess looking at the picture. So if I draw in my segments, those are my 4 intervals. And on each interval, I'm going to use the left-hand side to make an estimate of the height. And this is the best I can do because I've been given the graph and not a function. So let's go ahead and get those heights. So for my first rectangle, if that's 1 and that's 2, that would be 1.5. And this is about halfway between those two. So I'm going to estimate that this height is 1.75. So for my first rectangle, when I draw in that left-hand endpoint, my base is 1/2, and I'm going to estimate that the height is 1.75. For the second rectangle, that point is landing pretty perfectly on 1.5. So I'm going to draw in my rectangle and take my height to be 1.5. For my next rectangle in here, Now I need, again, a width of 1/2, but now to estimate this height, it's pretty spot on, halfway between 1 and 1.5. So I'm going to estimate that as a height of 1.25. And now for this last one, when I draw in my height on using the left-hand side, that looks like it's about halfway between 1.5 and 2 again. So that's right at about 1.75. That's what I'm going to estimate my height to be. And now I'm going to ask the really hard question. Just looking at my picture, do you think that what we just found is an overestimate or an underestimate of the true area under g of x? You can type it in the chat, overestimate or underestimate, just using the picture. I like the not sure. Thank you for the honesty. I think this looks like an underestimate. And the way that I'm thinking about that is, so here, this first rectangle, we've added a little bit more area than we should by using that rectangle. And here we've also added a little more area than we should. But if we look at these two, this is like, this last rectangle in particular is like way undercounting, right? Like that's a ton of area that we haven't included. So it's not always as simple as every single rectangle we draw is under the graph or every single rectangle we draw is over the graph. Sometimes we kind of have to look at the overall picture of this is how much we've undercounted by, and we've only overcounted by that little bit. So I think that's probably like as tricky as I can make one of these questions. Most of the time, we will probably be given the actual equation. So yeah, that's a good question. Is this less accurate than if we were given an equation? I would say that if the more accuracy my grid provides, then we might be just as accurate really as with an equation. If like I had a ton of little grid lines in here that we could estimate precisely. But yeah, in general, we're going to be more precise if we've been given an actual equation. Now there's another way that we can get more precise. And that would be, we're going to get a better estimate of the area if instead of just using 4 rectangles here, I used 8 or 16 or 1,000,000. Now I can't really draw, I can probably draw in 8. So do not try to take notes on this. It's not going to get pretty. But I'm going to try to draw in 8 just to look at what happens in terms of that overestimate, underestimate thing. So. Okay. Put my curve back in here. So if we were to do this and break it up into 8 intervals, well, now, if we do the same thing and we still use left-hand endpoints, when I draw those in, those little bits that I am, oops, went too far. Now, each time I'm drawing in, the bit that I'm off by in terms of my rectangle in comparison to the true area under the graph, each of these just got smaller. And if you can imagine, if I shrunk those in half again, then the little bits that we're off by get even smaller. So the whole reason that we need the sigma notation stuff is because we are going to add a limit into the mix. We're going to look at that limit as the number of rectangles we create goes to infinity. And for my boring function, I want to find the area from, let's go 1 to 4. So for starters, that area is a trapezoid. So we actually know what the area is. We can find it. I don't know if you remember how to find the area of a trapezoid, but it's kind of like the area of the rectangle, but you average the two heights. So here, if this is y equals x, then I know that this point is the point 1, 1. And I know this point up here is the point 4, 4. So if I find the actual area, no calculus involved, we're just using geometry here. The actual area of a trapezoid is the base times the average height. So in this case, the base of my rectangle, the base of my trapezoid here is 3 because I'm going from 1 to 4. And the average of the heights looks like I add them together, divide by 2. So the height on this side is 1, the height on this side is 4. So I'd have 1 plus 4 all over 2. What's that? 5 halves, 5 times 3. So 15 halves is what I get. That's the actual area. Now we're going to do a whole bunch of calculus to get the same answer. So if you like formulas, we can use a formula, but I want to talk through where that formula comes from for a minute. So far, we've talked about like, well, what if I have 3 rectangles or 4 rectangles or 8 rectangles? What if I'm going to make this really messy? Don't take notes for a second because I'm going to erase it. We're not going to do this next part. I'll turn you back. I'll clue you back in when it's time to take notes. So let's say that I had 17 rectangles. That number is terrible. Don't worry about it. We're not really going to do this. Well, if I had 17 rectangles that I was trying to put in here, then the width of each of my rectangles would look like 4 minus 1 divided by 17. Again, terrible. Don't worry about it. 4 minus 1 over 7, so that's 3 over 17. Now, I can't really draw 17 rectangles in here, so I'm going to fake it, and I'm going to call this 1, and I'm like giving myself a little bit more room there, and there's 14, and then I'm going to draw 17 rectangles. There's like my first one, my second one, my third one. I'm going to be really lazy. I'm going to call this my ith rectangle. And then my last one, my 17th rectangle. So these would look like, you know, some kind of rectangle-y thing. It's my fake picture. Well, if the width of each of these things is 3/17, then here I was in an x value of 1. So right here, I've moved over 3/17. So I'm at an x value of 1 plus 3/17. That's gross. When I move to this next spot here, I've moved 2 sets of 3/17. So that x value right there is 1, but now I've moved over 2 of the 3/17. So plus 2 of the 3/17. Hopefully we're getting the picture. On my third rectangle, that right-hand side, we started at 1 and we moved 1, 2, 3 sets of 3/17. Now, because we know we're going to be adding all of these areas up, and conveniently, we've talked about this new notation involving a sigma. It sure would be cool if I knew what the ith rectangle looked like. So for my third rectangle, the right-hand side looked like 1 plus moving 3 of the 3/17. So when I get out here to the ith rectangle, my right-hand side x value is going to look like 1 plus I of the 3/17. Now, just as a reality check, by the time I get to my last rectangle here, on the right-hand side, we know it should be 4. But if we're just like following this kind of rule that we've got set up, the right-hand side should look like 1 plus, well, by the time I get to my 17th rectangle, I've moved 17 of the 3/17. So I'd have 17 times 3/17. What do you know? The 17ths cancel. It works. 1 plus 3. I get 4. Math wins. You can imagine that this would get really messy for all the possible numbers of rectangles that we can shove in there. So here's the part where you want to start taking notes. So what mathematicians have done is they've said, well, let's just figure out what this formula would look like for n rectangles. And we won't worry about what n is equal to right now. We're just going to use n rectangles. Well, if we use n rectangles, then to find the width of each of those partitions, we'd have b minus a over n, or in our case, 4 minus 1 over n, and I'd get 3 over n. So that's going to be the width that we're moving each time when we're finding the x values. Well, it's going to work the same way as it did when we had that ugly increment of 3/17. It's just now my increment is going to be 3 over n. So if I start with a 1 here, because we were looking for the area between 1 and 4, the right-hand side of my first rectangle will have an x value of 1 plus 3 over n. When I get to the right-hand side of my second rectangle, I've moved 2 of the 3 over n's. So that's going to be 1 plus 2 times 3 over n. And for my third rectangle, I moved 1, 2, 3 of that delta x, or I've moved 1 plus 3 times 3 over n. And when I get to my ith rectangle, I'm going to be at 1 plus I times 3 over n. So I'm going to pause for a second because there are a couple of formulas that I want to make sure that you've got in your notes. The first one here is this right here. So if we're going to have n rectangles, then the width of each rectangle, or the delta x, is b minus a over n. Now the next one is sitting right here. So this is for a right-hand endpoint. And on that right-hand endpoint, if I were to give this as a formula, then my x sub I for a right-hand endpoint looks like, well, the 1 is where we started, and we usually call that start and stop A and B. So the 1 is where we started, so this looks like A plus, we've moved over I of the delta x's. So I could write that as I delta x, or I could write that as A plus I, and then put in the formula for delta x, B minus A over n. And that I'm putting the X in quotations because that's like the X value for my generic ith rectangle. When we move that forward and think about, well, how would I actually find the area? Well, I'd add up all these little pieces of area. And an addition problem is a sum. So that summation would go from I equals 1 to n, because I've got my n rectangles in here. And I'd have the base and the height of that rectangle. Well, the base or the width of that rectangle is my delta x. And the height I would get by plugging this into the formula for the equation. So a plus I delta x. And that is going to give me the sum of all the rectangles for whatever n value we specify. I'm going to erase my fake picture and actually work this out for this problem. So I'm erasing my fake picture of the rectangles. And hoping that I've got enough space on here to work it out. I think it's going to be close. Okay. So this true actual area here, or rather our estimate, no matter what the number of n rectangles was. So my sum is going to go from I equals 1 to n. We know what our delta x is. That was 3 over n. Then I need f of a plus I delta x. Well, my function is just y equals x. So the function part isn't too bad. And what we're going to put in here is 1 plus I times 3 over n. And this is the thing that we're going to add up. Now's where life gets fun. So the whole reason that we were talking about sigma notation and practicing with sigma notation is so that we can attack problems like this. The first thing, and something that I think is really confusing, so we've got i's and n's, but which one is really the variable? So when we've got sigma notation, it's the letter down here on the bottom that is our variable. This n, I haven't told you how many rectangles it was, but it's a fixed number, right? Maybe it's 4 rectangles or 17 rectangles. So I didn't tell you what it is, but it's a constant. So anywhere the n shows up in here, we treat it like it's a constant. And that can be confusing when you're first starting out with these. So the I is my variable, the n is a constant. So the first thing that I'm going to do in terms of our summation rules is to notice that 3 over n, that's a constant, and we can pull it out in front of our sigma. I know it's weird to think of n as a constant, but it is in this case. So I'd have 3 over n, and now we're going sigma from I equals 1 to n. And I would just be left with the 1 plus I times 3 over n. So my next summation rule that I'm going to use is I've got addition between 2 pieces, so I can break that apart. So I've got my 3 over n, and I'm going to take that summation and I'm going to break it apart. So the first one becomes the sum from I equals 1 to n of 1. And then the second part, I'm going to do 2 steps at once here. But this one, when I pull that out to be its own sigma notation, 3 over n again is a constant. So I can pull this 3 over n in front of this summation, and I'll be left with I from 1 to n. Thanks for hanging with me. We're getting close. Now I can apply those sigma notation rules that we were talking about before. So I've got 3 over n here, if I take 1 plus 1 plus 1 plus n times, I'm going to get n. Here I'll have that 3 over n that was sitting out in front. And then our formula for the sum of I from 1 to n is n times n plus 1 all over 2. Now we're almost there. I thought I had enough space. I don't quite have enough space, so I'm going to need to erase my generic formulas here. Luckily, these are in the textbook, and they're also in Shuttery's notes for Friday. Got n over n. I'm going to cancel that. Oh, question about, do you have to memorize the formula for the sum of I? I don't know. So far, it's been given to you on every web work problem. I'm pretty sure it's going to be given to you on the test. Worth asking maybe as we get closer to that first thing, but on all the web work problems, so far it's been given to us. So I'm going with that. So if I look at this, now I said that we were doing this for n rectangles, and n could stand for anything at all. But if I want to find the true, actual, correct area, then I have to put an infinite number of rectangles in there so that the width of each of them becomes so small that there is no error between our rectangle area and the area under the curve. So now that we have this expression, I'm going to take the limit as n approaches infinity of this thing. And I'm going to go ahead and distribute in the 3 over n. So I'd have 3n over n plus, and if I distribute this in here, oh, how about if I do this? That n over n is going to cancel, just to simplify my life a little bit. And I'm going to take that 3 over n and distribute it in here. So I'll have 3 times 3 and get 9. We've got that n plus 1 on the top, and on the bottom, I'll have a 2 and another n. Cool. N over n cancels. And this, I don't know how much fun y'all had with limits last quarter in 17A, but I'm going to go ahead and do a little quick algebra thing and split this up into 2 separate fractions so that I have 9n over 2n plus 9 over 2n. Because on this one, my n's will cancel. And on this one, as n approaches infinity, 9 divided by infinity is going to go to 0. So when I'm done with the limit, I just have 3 plus 9 over 2. Now that doesn't quite look like what we had up here, but it will be momentarily, because if I get a common denominator between these two, that 3 is going to turn into a 6 halves plus a 9 halves, and then I'm going to get 15 halves. This is the point where you should be asking yourself, if we could do that, why did we just do this? And the answer is, for this problem, we shouldn't. If you can just straight up look at the thing and find the area using geometry, you should definitely do that. But for functions where we can't just use the geometry, this is mathematically the way that we can find the true correct area. It is 10:50, so I didn't quite get to fundamental theorem of calculus. That'll have to wait until Wednesday. But on Wednesday, we're going to take this process and we're going to get a shortcut for it.